going to be looking at how to solve polynomials, how to find our zeros of our polynomials that are not quadratics. With quadratics, we can go directly to the solution using the quadratic formula. But when we get to ones that are of degree 3, 4, 5, or higher, we don't have a direct method. So we have several tools that help us find those roots or to help make it easier to find those roots. So we're going to be looking at several of those in this lesson. One of the first things we're going to look at is called the rational root theorem. This helps us narrow down our solutions if we have rational zeros. Now, the rational root theorem does not guarantee that we have any zeros that are rational. All it does say is that if we have rational roots, then they will be of this form. So, and most of the time, you will have at least one rational root. And so it helps you get your equation down to a form that you can solve it. Now what this says is if you have any rational zeros, then they will be of the form where they are a factor of the constant term divided by a factor of the leading coefficient. So we're going to look at how to go through and list all of our possible rational roots. Let's take this polynomial. F of x equals x cubed plus 2x squared minus 5x minus 6. Now all we're going to do right now is just list the possible rational zeros. If it does have a rational zero, then it will be of these numbers. So we take the factors of the constant term. Well, the factors of 6 are 1, 2, 3, and 6. And we don't know, it could be a positive 1 or a negative 1. Positive 2, negative 2. Positive 3, negative 3. Positive 6, negative 6. So those are our factors of our constant term. Then we go to the factors of our leading coefficient. Well, our leading coefficient is 1, so the only factors of 1 are 1. So we would divide each of these numbers by 1, which will give us 1, 2, 3, and 6. So out of all the millions and billions of rational numbers, if this has a rational solution, it will be one of these 8 numbers. And so we've narrowed it down some. Let's take this function. F of x is equal to 4x to the 5th plus 12x to the 4th minus x minus 3. Okay, we want all of our rational roots, all of our possible rational roots. Now, our factors for 3 are 1 and 3. Our factors for 4 are 1, 2, and 4. So what we're going to do is take every factor of our constant term and divide it by every factor of our leading coefficient. So that would give us, and I usually like to take these and divide them first by our number 1. So that would give us plus or minus 1, plus or minus 3. Then we're going to divide each one of them by 2, so plus or minus 1/2, plus or minus 3/2, and then we'll divide each one by 4, plus or minus 1/4, plus or minus 3/4. So if we have a rational zero, then it will be one of those numbers. Now, let's look at how we would use this then to start finding our solutions. Let's take f of x is equal to x cubed plus 8x plus 11x, 8x squared, plus 11x minus 20. Now, we know that we have 3 roots. We don't know if they're rational or irrational, real or imaginary. We just know that we have 3 roots. So we want to see if we can narrow down of how we would go about finding it. Well, we're going to take our factors of our constant term, which would be 1, 2, 4, 5, 10, and 20. divide it by every factor of our leading coefficient. So we come up with plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 10, and plus or minus 20. So we've narrowed it down to those numbers. We're going, in a little bit, we'll look at another way to narrow it down even further, but right now we're just going to deal with this. So we're put our coefficients. We're going to do synthetic division, and we know if we get a remainder of 0, then that was a factor. And we're just going to start. I usually like to start with positive 1. So we have 1. 1 times 1 is 1, plus 8 is 9. 1 times 9 is 9, plus 11 is 20. 1 times 20 is 20, plus negative 20 is 0. So 1 was a root. If it hadn't been, then we would try 2. If 2 didn't work, we would try 4. And we would try them, and then we could go back and try the negative ones. We try them until we find one that worked. Now, what this did was it gave us a reduced equation of x squared plus 9x plus 20. Well, that's a quadratic. We know how to solve it. In fact, we can factor this one. Factors of 20 that add to be 9, 5 and 4. Signs are the same. They're both positive. Setting each factor equal to 0, we get x equals negative 5 and x equals negative 4. And then we found through our synthetic division that x equaled 1. So there are our 3 solutions, or our 3 roots. And so we used our rational root theorem to narrow these down just a little bit. Let's look at another one. This one we're going to look at one that's to the 4th power. So let's say we have x to the 4th minus 6x cubed plus 22x squared minus 30x plus 13 equals 0. So we want to find our roots. Now, let's narrow it down because we know that there's a whole bunch that we could have, and actually we have 4 roots. So we're going to take our factors of our constant term, which would be plus or minus 1 and plus or minus 13, and divide it by factors of our leading coefficient, which is just 1. So in this case, we're down to 4 numbers. So we've got 1, negative 6, 22, negative 30, 13. And let's start with 1. So 1 times 1 is 1, minus 6 is negative 5. 1 times negative 5 plus 22 is 17. 1 times 17 minus 30 is negative 13. 1 times negative 13 plus 13 is 0. So 1 was a root. So we know that x equals 1. Now, what we have here is a reduced equation. But this is x cubed minus 5x squared plus 17x minus 13. So we need to find our roots for it. Well, we actually have the same choices because our constant term's 13 and our leading coefficient's 1. So we're going to take what we call this reduced equation, and we're going to do the same thing. So I'm going to start with 1 again, because you can have a solution more than once. 1 times 1 is 1, minus 4, negative 4, plus 13, 13, and 0. So 1 was a solution. Now you don't always know when you start, so I just usually start with 1. We'll have some things that'll help us in just a little bit later of giving us better ideas of where to start. So it may have just looked like, oh, I knew exactly what that was going to be. I didn't. I just started with 1. If it hadn't worked, then we would have tried the 13 or the negative 1. Now, once a number doesn't work, then it won't work even in the reduced equation. So if we had tried 13 and it didn't work here, up here, then it wouldn't have worked down here in the reduced equation. Now what I have left then is x squared minus 4x plus 13 Now that's not factorable, but I can use my quadratic formula and solve for x because now I'm down to a quadratic. So x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So we have 4 plus or minus the square root of 16 minus 52 over 2, which is 4 plus or minus the square root of negative 36 over 2, or 4 plus or minus 6i divided by 2. Now each of those can be divided by 2, so we end up with 2 plus or minus 3i. So there's our 4 solutions, 2 plus or minus 3i. So we can use this to go about solving. And one of the things that you're going to find is, as we went through, we already mentioned a couple of things. First of all, we mentioned that if we're the fourth root or the fourth degree, then we're going to have 4 solutions. We don't know what kind of solutions, what sets they'll come from, but we know that we have 4. Another thing that we also know is if we get a complex number, then we will get conjugates. If we get 2 plus 3i, then we automatically have 2 minus 3i. These are some properties of our polynomials that will come about. So if you find that you have one complex number, then you know that you're automatically going to have 2 complex numbers. And then we know about the degree. Now let's look at 2 theorems that are important. One is the fundamental theorem of algebra, which goes along with what we just said. If f of x is a polynomial of degree n, where n is 1 or greater, then the equation f of x equals 0 has at least one complex root. If n is 1, it's going to have one complex root. If n is 2, it's going to have 2. If n is 3, it will have 3. Whatever the degree is determines how many roots we have. But you are guaranteed at least one complex root if n is greater than or equal to 0. Now remember, your complex numbers include your imaginary, so it doesn't guarantee a real root, but it does guarantee a complex root. Then we have what we call our linear factorization theorem. And it just says that an nth degree polynomial can be expressed as the product of a non-zero constant and n linear factors. We can use this to go about finding an equation when we know the solutions, but we don't have the equation. And as we get into higher degrees, then this becomes a little bit more difficult to do. So we want to look at this. Let's say that we have a equation. We know it's going to be of the 3rd degree, which means our highest exponent will be 3. We know that negative 3 is a solution and I is a solution. These are roots. And then we also know that f of 1 equals 8. So this is the information. Now we're to come up with the equation. Well, we know that we have 3 solutions because it's a 3rd degree. One thing we just mentioned is if you have a complex root, then you automatically have its conjugate. So if we have x equals I, then we also have x equals negative I. So there are our 3 roots. Now what we don't know is how wide this opens. We can have a lot of equations that give us cross the x-axis at the same but open at different rates. So what we're going to look at then is we can write this as f of x is equal to a, that's your non-zero constant, times these factors, these linear factors. So if these are the roots, that means x equals negative 3, so the factor would be x plus 3. We would add 3 to both sides and get x plus 3 equals 0. Remember, you set your factors equal to get 0 to get your roots. So we're wanting to go back to the factors. And x plus I and x minus I. These would be our factors. So we've expressed it as the product of a non-zero number and the factors. Now we want to come up with the equation. So we're going to multiply this out. I'm going to start by multiplying my complex numbers. And when we first looked at multiplying complex numbers and conjugates, we actually had a theorem that said if you multiply conjugates, a plus bi times a minus bi, you're going to get a squared plus b squared. You're going to get this number squared plus the coefficient of your I squared. So if we multiply these, then we're going to get x squared plus, well, my coefficient's 1, and 1 squared's 1. Then we can distribute. We have x times x squared is x cubed plus x plus 3x squared plus 3. And we could write that in descending order. That would be x cubed plus 3x squared plus x plus 3. Now, that gives us an equation, but it doesn't tell us the a. It gives us what we might call a parent equation for this, or a family of equations. The a will give us a specific one. So that's where we go back and use this piece of information. F of 1 equals 8. So we're going to find f of 1, which means we're going to take our equation. Wherever there's an x, we would plug in 1. And when we do, we're going to get 8 for an answer. Well, we still don't know a, but we've got 1 plus 3 plus 1 plus 3, which adds up to be 8a equals 8. So a equals 1. So now we have our equation, a equals 1. So if we multiply that out, then we're going to end up with the equation f of x is equal to x cubed plus 3x squared plus x plus 3. So this is the equation that will give you these roots and go through this point. All right, let's look at one more like that. Okay, let's look at this problem, and we're going to go through again with it and find our equation that will give us this information. First of all, we wanted an equation of the 4th degree. We want n to be 4. We want to have -2, -1/2, and I as zeros, which means then that we will also have -I. And we want it to go through the point 118. When x is 1, we want y to be 18. So we can start off by writing it as a product of a non-zero constant times the factor. So remember, for the factors, this is x equals -2. And, so you can set it equal to 0 and solve, or you can remember your factors are to be in the form of x minus c. So x minus a -2 would be x plus 2. X minus a -1/2 would be x plus 1/2. X minus I and x plus I. Now we're going to go through and multiply this out. And so what we're going to have, if we multiply these first two, well, we've got x squared plus 1/2 x plus 2x plus 1. Just doing your distributive property. These are conjugates, so it's going to be the first term squared, x squared, plus the coefficient of the I squared, so that's plus 1. Combining any like terms, we have x squared. We have 1/2 x plus 2x, which would be 2.5 x, or 5/2 x, plus 1, times x squared plus 1. Now, what we're going to need to do is to multiply this. So x squared times x squared is x to the fourth. X squared times 1 is x squared. 5 halves x times x squared would be 5 halves x cubed. 5 halves x times 1 is 5 halves x. 1 times x squared is x squared. 1 times 1 is 1. And combining our like terms, we have x to the fourth. We have 5 halves x cubed. We have x squared plus x squared, so 2x squared plus 5 halves x plus 1. Now, we need to figure out what a is. To do that, we use our other piece of information up here, that f of 1, meaning we're going to substitute in 1, so 1 to the fourth plus 5 halves times 1 cubed plus 2 times 1 squared plus 5 halves times 1 plus 1, and that will give us 18. So a times this would be 1 plus 5 halves plus 2 plus 5 halves plus 1. And if we add this up, 5 halves plus 5 halves is 10 halves, or 5, plus 1 is 6, plus 2 is 8, plus 1 is 9. So we have 9a equals 18, so a equals 2. Now we can go back to this equation that we found, and now we know what a is. So if we write it in that form, a is 2, and our equation was x to the fourth plus 5 halves x cubed plus 2x squared plus 5 halves x plus 1. And now if we distribute the 2, we have 2x to the fourth plus 5 halves x, whoops, excuse me, I didn't distribute there. So I would have 2 times 5 halves would be 5x cubed plus 4x squared plus 5x plus 2. And so now I have the equation that will give me those solutions and go through that particular point. So that's dealing with our linear factorization theorem, and that's how we go about coming up with our equations. Now, the next thing we want to look at is another way we have of, when we're trying to solve our equation, of kind of narrowing down some of our choices. We looked at our rational root theorem, which gave us the possible rational answers. Well, we also want to deal with what's called the Descartes rule of signs. And when you first read this, it sounds a little complicated, but it's very easy to use. It says that the number of positive real zeros, notice that that's positive, real, and it's real. It's not rational. This isn't the rational root theorem. This is saying how many positive real zeros we have, is either the same as the number of sign changes of the function, or less than the number of sign changes by a positive even integers. So you would start subtracting 2. And you go down and you will know how many positive real zeros you have. To find the number of negative real zeros, then what we do is we go through and we're going to find f of negative x. Wherever there's an x, we'll substitute in a negative x. The number of negative real zeros will be the same as the number of sign changes of f of negative x, or less than the number of sign changes by a positive even integer. So let's look at what that means, and it'll make a little bit more sense once we start looking at some examples of what this means. Okay, let's say that we have the equation f of x is equal to x cubed minus 5x squared plus 17x minus 13. We're just wanting to know how many uh, real solutions we have. So we look at our number of sign changes. If we look at these, okay, this term was positive, this term was negative, so we had a sign change. This was negative, this was positive, so we had a sign change. This was positive, this was negative, so we had a sign change. So we had a total of 1, 2, 3 sign changes. So we're going to have 3, the number of sign changes, or that number less a positive even integer. Well, our positive even integer is 2, so 3 minus 2 is 1. So we're going to have 3 or 1 positive real roots. Okay, we want to find out then, well, how many negative real roots can we have? Because we know we have 3. So we have we can have 3 positive roots, or we could have 1 positive root, and we need to know, well, what other kind of roots do we have? So we're going to take our function, wherever there's an x, we're going to plug in negative x. Now, basically what's going to happen is any term that was to an odd exponent, that term of that sign, the sign of that term is going to change. So we have negative x cubed would be negative x cubed. Negative x squared is x squared times negative 5 is negative 5x squared. See, that term sign didn't change. 17 times negative x is negative 17x. That was an odd power. It changed. Minus 13. Now, as we go through and look at this, we didn't have any sign changes. So this means we're going to have 0 negative real roots. Now, if you want to go through and summarize what we know then, our possibilities is we're either going to have real roots or imaginary. And in the imaginary, we know that we would have conjugates. In the real roots, we're either going to have positive real roots or negative real roots. Okay, this is said that there's a possibility that we're going to have 3 positive, so we would have no negative and no imaginary. That takes care of our 3 roots. Now, we could have had 1 positive root. We still have no negative, and that would leave 2 imaginary roots that we could have had. So it helps us have a way of narrowing down the number and the kinds of roots that we have. Let's look at a different one. Let's say that f of x is equal to x to the 4th minus 2x cubed minus 5x squared plus 8x plus 4. We just want to know the number of types of roots that we have. So we'll start with our sign changes. We went from a positive to a negative, so that was 1. Here we went from a negative to a positive. So we had a total of 2 sign changes. So that says we either have 2 or we reduce it by an even number, 0. So we have 2 or 0 positive real roots. If we went through and found f of negative x, and after you've done it a while and you see that it's only the signs to the odd power that changes, then you're able to just write that down as you go. But if not, then go ahead and work it out. So this would be x to the 4th. This would be negative x cubed times negative 2, so positive 2x cubed. This would be x squared times negative 5 is negative 5x squared. 8 times negative x is negative 8x plus 4. So here we have a positive, positive, negative. So we have a sign change, negative, positive. So that means we have 2 or 0 negative real roots. So that would give us Descartes' rule of signs. Now again, this second equation, the only thing we're using it for is to find out how many negative roots we have. We're not going to use it for anything else. Okay, We're going to then go through and put this all together to solve some equations. And I'm going to do that on a different video just because it does take a little while to do this. And I want you to understand before we ever start this, there is no quick, fast way to do this. There's not a direct way to find these 4 roots. There are methods that we have that will help us find the roots. And we're going to use those. We'll use some to eliminate possibilities like the rational root theorem and Descartes' rule of signs. We will use synthetic division so that we get a remainder of 0. That tells us when we have a root. We'll use that intermediate value theorem that if our remainders change signs, then that lets us know that we had a 0 somewhere between the 2 x values. We'll use a lot of logic, but some of it's just trial and error, and there's not a quick way. It does take you a little time to do these. So we will stop here on this one, and then we will do another video where we're just taking about 3 problems and going through and solving them using our different techniques.